So let's see what I can do, right? So let's go step by step. The first thing that we will try to do is tackling the false positive. So let's try to tackle the false positive rate, which is in this case 0.4, right? So that's the false positive rate that I have. So the idea that we are going to use to tackle the false positive rate is the following. This is the first idea. So we will AND several hash functions. What do I mean by that? Now we know that, let's say if it's the Thar style, then h of x is A transpose x plus b by w for some A and b, which we have already spoken about. Now what I am going to do is I am going to create a g of x, which is an concatenation of multiple such hash functions, right. So I am going to call g of x as h1 of x, h2 of x dot 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 hk of x, where for all I, hi of x is a I transpose x plus pi by w. That is, I don't just use one random vector, but then I use multiple random vectors, right. So a1 through ak, b1 through bk. Now we are getting even more closer to JL style, right. So because JL was using k different random vectors, right. So here it serves a slightly different purpose, but they are connected. So let's see what happens in this case, right. So now then what will I do, right. So if I did this, so then I have like a k dimensional space where I am searching for where I am hashing to, right. So it's no longer like a one dimensional one number, it's k numbers. So which means that a collision happens when if I take 2 points x and y, and then all the k hashes match. That's why I call this the ANDing, right. So you're ANDing several hash functions. If there are two guys who are close by, so then or far apart, doesn't matter, right. So if I take x and y, h of x, g of x and g of y should match, which means that h1 of x and h1 of y should match, h2 of x and h2 of y should match until hk of x and hk of y, right. So now why are we doing this, right. So now if I ask, right, so what is the false positive rate for this hash function, right. So what is the false positive rate for this hash function? Well, if I have a query q, right, so then I have some g of q, which is going to be h1 of q, h2 of q, and then hk of q, and these all the h's are all independent of each other. Now I want to ask, if q and x are far apart, right. So that is the distance between q and x is greater than c times r, then what is the chance that they get hashed into the same bucket? So with one hash function it is 0.4, right. So and it's the same hash function that I am repeating, same randomness, random distribution from which I am repeating the hash functions k different times, which means that for each hi is going to be RCR P1 P2 sensitive, right. So which means that if I put k of them together, then what would be the false positive rate, right. So now these two guys will collide with probability 0.4, these two guys will collide with 0.4, these two guys will collide with 0.4, and then for all of them to collide with 0.4, well, what would be the false positive rate? Well, it should just be P2 power k. That's my false positive rate now, right. So for example, if it was 0.4 when k equals 1, that is when I am using just one hash function. When k is 2, then it suddenly becomes 0.16. When k is 3, it becomes 0.4 into 0.4 into 0.4, which is 0.064. And as you can see, the fraction of or the false positive rate kind of decreases really quickly, right. So now I need to know how many such hash functions that I should AND, right. So, so what is my goal? My goal is, if the false positive rate is more, then so roughly if the number of the number of false positive points is order of n, right. So, I am just going to think of it as n for the moment. So, for a given k, for any k, right. So, expected number of false positives collisions, how many bad guys will be there in the same bucket that the query hashes to, is going to be roughly n times p2 power k expected number. I am calling this n because I am thinking of it as order of n, right. So, we had n was 10,000, but then there were 8,000 points outside the good outside the bad, 8,000 bad points, but 8,000 I am thinking of it as roughly as n, right. So, order of n, some small constant times n, but still the constants do not really matter. So, it is like n into p2 power k. Now, what do I want this to be, right. So, I want this to be a constant, right. So, meaning I want only, I do not want the number of bad guys to depend on n at all, right. So, the number of bad guys that I would see on an average should be some, if it is 10 it is okay, if it is 5 it is okay, if it is 1 it is okay, right. So, it is some constant number, it should not depend on the number of points that I have, right. So, but now I have the power to choose k, right. So, I can AND it how many ever number of times I want. So, I have the power to choose k. So, let us say I choose k such that n into p2 power k is just 1. When I say 1, it is order of 1, right. So, but for now let's think of it as just 1, right. So, I just want one false positive. So, which means what should k be? Well, I can take the logarithm on both sides. Well, before that, this means that this implies p to the k is 1 over n, which means k log p2 is log 1 over n, or k is log 1 over n by log p2. So, now n is greater than 1, of course n is a large number, p2 is also less than 1. So, 1 by n and p2 both will be less than 1. So, the logarithm of a number which is less than 1 is going to be negative. So, I can write this as minus log, just to keep the positive value inside the log, divided by minus log 1 by p2. So, which is, and the minuses cancel, so which is log n by log 1 by p2, right. So, I should choose, if I want constant false positive rate, then I will choose k as log n by log 1 by p2. That is what this means. Just to give a sense for what kind of a number this is, right. So, so in our example, in our example, what does this mean? K is, we would set n was 10,000 for us, 10,000 by log 1 by 0.4, right. So, this is log 10,000 by log 2.5, which if you do the calculation, I have done this already. So, this is something like 10 point something. So, k is roughly like 10. So, what that means is that if you have 10,000 points, and then if you have a hash family which is P1, P2 sensitive, where P2 is 0.4, then if I repeat that hash family 10 times, then my false positive rate is going to be constant. It is just 1, right. So, that is what this means. Now, at this point, you should already have a question, right. So, now, okay, so we have repeated this, and then our false positive rate goes down to a very small number. In fact, what is exactly the false positive rate? Well, the false positive rate for our example is going to be 0.4 power 10 now. That is what the false positive rate is, right. So, this is P2, this is k. 0.4 power 10 is something like 0.000104886, right. So what is this? This is the chance that the query point and a bad point and a single bad point mapped to the same bucket, which is a very small chance. And if there are 10,000 points, then the expected number of bad points that I would see is 10,000 times this, which is roughly 1, right. So I'm not going to see too many bad guys, right. So that's the numerical thing, right. So if you like numbers more than just symbols. Okay, so now a natural question that we have to ask at this point is, okay, so earlier it was P1, P2 sensitive, and suddenly we said that, well, to reduce the false positive rate, I have done this AND operation, but that, of course, that helps us in the false positive rate, but how does that affect the true positive rate, right? So there should be some effect on the true positive rate, obviously, right? So what is that effect, right? So what about true positive rate? Can you calculate the true positive rate for this example that we had? It's not too hard, right? So it's the same idea, right? So I'm doing the ANDing. If it's doesn't matter if it's a good point or a bad point, right? So all the hashes should match. But for one hash to match, the good point has a higher probability. It's not 0.4, it's 0.8, right? So now if I repeat the hash 10 times because I want to get the false positive rate down to a constant overall, so then the true positive rate also suffers, right? So the good guys, so the expected or the chance of a good guys have probability now 0.8 power 10 of matching, right. So which is if you do the calculation, so this is something like 0.1074, right. So which means what this says is that the true positive rate TPR suffers. This kind of means then that if I had originally 10 good points, now if I want all the expected number of good points, good guys, whose hash for all the 10 hashes will match all the 10 hashes for the query point, is going to be now 10 times, because there are 10 good guys, 10 times 0.1074, which is like 1, right. So which means that there is only going to be 1 or 2 good guys who will be retained. The remaining are lost, right. So so while the false positive, so you are now going to have, right. So basically the number of so the expected number of good guys, good points, okay, let's be a little bit more formal. So good points, not guys, though, yeah, is going to be, again everything is rough, right. So 10 times 0.1074, roughly 1. So what does this mean? This means that in the bucket that we are looking at for the query point, there's going to be one good guy and then one bad guy, right. So out of 8,000 bad guys or 10,000 bad guys, only one guy matches the hash function of the query, and only one good guy matches, right. So which means that the number of distance computations I need to do in the bucket is very low. That's a good thing, right. So but what is bad is that there's a high chance that I might lose the actual nearest neighbor, right. So because the true positive rate is small. So now this is a tricky situation, right. So because on the one hand we don't want to do too many calculations, so that we should not have too many bad guys, so we have to bring down the false positive rate. But by bringing down the false positive rates and bringing down the number of bad guys, we should not lose out on too many good guys also. But then just by the virtue of the fact that we are doing ANDing to bring down the number of bad guys, the good guys quality is also going to suffer. So we cannot just stop here and say that we have solved the problem, right. So in fact this is worse than what we pretty much had earlier, right. So at least in the earlier case we had 8 out of 10 good guys in retained and 30 to 200 out of 8,000 bad guys retained. So I might have to do more calculations, but at least I would find the good guy, right? So the nearest neighbor with a high probability. Here I will do very less calculation, but I will not find the nearest neighbor, right? So the chance that I'm going to find the nearest neighbor is very low, right? So now there are several, things that have to be delicately balanced here, right? So the amount of computation I do, the chance with which I will find the good guy, both of them have to be balanced somehow. And we have two extreme cases. One case, a lot of computation, right? So which is the 0.8, 0.4 case, high computational cost because a lot of bad guys, and also high chance of finding nearest neighbor approximately, right. So on the other hand, here we have 0.1074 comma very small number, what is that, 0.000104886, very low computation because very few guys are going to match the hash on an average, low chance of finding nearest neighbor, right. So these are two extreme situations that we have, and we have to find a middle ground for this. And what we will do now is do a step 2 of of whatever we have done so far, so that we will find hopefully a middle ground, right. So where the computation is not going to be as slow as the right hand side, but the chance will significantly improve with increasing computation, right. So how can we do that?